This video shows an example of trig substitution using the tangent. So back in Calculus 1, when we studied arc length, a problem came up where you didn't know how to find a final solution because the integral was too difficult for Calculus 1. So we're going to find the arc length on the curve f of x equals x squared from x equals 0 to square root of 3 over 2. Now, in case you don't remember about arc length, here is the derivation of the formula that you can see here, and here is the final formula for arc length on a curve f of x from A to B. Okay, but this is a trig substitution problem, so we're not going to go over that derivation, but there it was on the screen. Okay, so here's the problem at hand, and this is going to be pretty long, but it does show all the tricks of the trade through it. So, setting up the arc length formula, you have the limits of 0 to square root of 3 over 2, 1 plus f prime squared, and that's an a squared plus x squared type square root, so we're going to use the tangent. That's when you use the tangent substitution. Okay, and what we need to do is to factor out this 4 that you get by expanding this, squaring this out. You have a 4 there, so we're going to factor out the 4, and inside you're going to get 1/4 plus x squared, and then of course the square root of 4 here comes out to be 2, and you'll have 1/4 is 1/2 squared and your x squared. So this is what your form looks like right here, and that's matching up to the proper form to use with trig substitution using the tangent. So you make your triangle over here, and you're going to use a tangent. So you want the x to be here, so the tangent of the angle there will be x over 1/2, because you have your 1/2 in here, and so you need, on the hypotenuse of the right triangle, you need to have it be square root of your 1/2 squared plus x squared. So this is matching up to your integrand. So for that to happen, you need to have x divided by 1/2 to be the tangent. Alright, so you're over here, tangent theta equals x divided by 1/2. So x is 1/2 tangent theta, so dx d theta is 1/2 secant squared theta, and we're now going to convert the limits for this substitution. When x is 0, tangent of theta is 0 according to your formula right here. When x is 0, tangent theta is 0. That implies from 0 to 2 pi that theta is 0. And when x is square root of 3 over 2, to convert over that integration limit, then your tangent, according to the formula up here again, would be x over 1/2. So square root of 3 over 2 divided by 1/2, which is square root of 3, and that converts to theta is equal to pi over 3. And in case you forgot why that would turn out to be pi over 3, if you have your pi over 3 angle right here on this unit circle, the point on the angle is, the terminal point is 1/2 comma square root of 3 over 2, and that corresponds to the tangent of that pi over 3 being square root of 3 over 2 divided by 1/2 y over x. So that's why that is. Okay, and now we're going to make all the substitutions. So your x squared right over here, this is your x squared. Okay, well, x is 1/2 tangent theta, so that converts over, and your dx is your 1/2 secant squared theta d theta. So that's this, and your substitution limits are 0 to pi over 3, and you have the 2 coming down from there. Okay, so just take a look at that again. This integral here converts by trig substitution using tangent to this integral here. Now we got to figure out this integral, and that's not easy. Alright, so we factor out a 1/2 squared out of here, and that became this, and inside I had 1 plus tangent squared theta and the 1/2 secant squared theta d theta out here. I took the square root of the 1/2 squared to get your 1/2 right there. Then 1 plus tangent squared by trig identity is equal to secant squared, and you still have this stuff out here. Then you take the square root of secant squared and you get secant, and when you multiply that with secant squared you get secant cubed. But what happened to the 1/2? This 1/2 combined with this 1/2, which is 1/4, multiplied onto the 2 to give us 1/2. So now here is your integral right here. Now that might look simple, but it's not. So now we launch off in a whole another integral to try to figure out that answer. So let's just take the integral of secant cubed. Let's just take that off to the side and see what that is before we figure out the rest of this. So the trick is to split apart the secant. You've seen that kind of trick before. We're going to use integration by parts. V is secant, du is secant squared theta d theta. So differentiating dv is the derivative of secant is tangent theta secant theta. You can prove that to yourself by using secant theta as 1 over cosine and then differentiating and simplifying, and you'll get this. Integrating up from du of secant squared comes back to tangent theta. So now we're just working out this secant cubed, and you use the parts formula and plug everything in. You get this. I multiply the tangents together to get tangent squared. Now you're here. Now use the trig identity. Tangent squared is secant squared minus 1. And I'm doing that because when I then multiply in the secant, I'm going to get secant cubed minus secant, which then I'm going to split up this integral because I'm going for a boomerang type, which I'll just show here. So I split up the integrals. Now this one right here, integral of secant, you did this before when we were reviewing over Calculus 1 substitution method, and that turned out to be log absolute value secant theta plus tangent theta. So then we recognize the boomerang mechanism happening here, which is that this subtraction of secant cubed will be able to be added to both sides, integral of secant cubed. And so on the right hand side you will end up with this 2 integral of secant cubed, and that is equal to what we had here on the right hand side. That's right here. Dividing by 2 throughout gives you here. So that's the antiderivative for secant cubed. Now back to the original problem. The original problem had this integral here, is where we left it. So I plug in what the integral of secant cubed was, which is all this. Evaluate from 0 to pi over 3, and of course the 1/2 is coming from here and here. Then I factor out a 1/2 multiplied by the 1/2 already, and we have 1/4 out there. Now I'm going to evaluate from 0 to pi over 3. And in case you don't know what the tangent secant is of that, here's your pi over 3 angle. The terminal point on the terminal side is 1/2 comma square root of 3 over 2. So the tangent is square root of 3. That's right there. Secant is 2 because cosine is 1/2. So 1 over cosine, which is the secant, is 2. And then in here secant was 2. Tangent was square root of 3. Subtract evaluation at the lower limit. Well, tangent of 0 is 0. And so that knocks out that whole first term, plus log of secant. The secant of the angle is the secant for a 0 radian angle. That's cosine is 1, so secant is 1 over 1, which is 1. And tangent is 0 divided by 1, because that point there is 0, 1 comma 0. So y over x is 0 divided by 1, which is 0. So you get 0. So that leads you down to this next step. I distributed in the 1/4 onto all these. And then